if you're taking calculus 3 or are going to take or took calculus 3, you've been told that the gradient is the multivariable equivalent of the derivative, and it is the vector field of the vector of steepest descent. I don't like this. I mean, this feels hacky, and it is hacky. It's not really true. And what led to my understanding of what the multivariable derivative actually is, which is the Jacobian, and what a derivative is in general, was this book, An Introduction to Geometric Algebra and Geometric Calculus. I don't have a PDF. I only have the physical version. I didn't really. I couldn't find it online as a PDF outside of buying it, and at that point, I'm just gonna buy the physical book. Okay. This was the textbook. This right here, this calculus textbook, was the one I had to use for school. The way it got, I don't like the way it got the gradient. Like, it took the single variable definition, which is already flawed. I mean, I'm not sure if I'm allowed, if I'm knowledgeable in math enough to say that the single variable definition is flawed. But I personally think this definition right here is a way better definition for what the derivative should be. Like, it's more intuitively, like, you can understand it better. So what it does is it takes the single variable definition. It says if h is a vector, we can't actually divide by vectors. So what we're gonna do is, they do some algebraic manipulation, and they get to this. And what really irks me is, this sort of dot product. Why is a dot product there? Why isn't it any other product? Yeah. So in the book I got, the other book, is it in chapter 2, it sort of went through a review of things you were already supposed to know. And when it got to derivatives, it basically just said that a derivative is a linear transformation that approximates the function at point x. So the derivative f prime x, that's a linear transformation. F prime is not a linear transformation. F prime of x is a linear transformation. All right, that should act on h. Right? If you don't know what a linear transformation is, it's just something that follows these 3 rules. All right, 0, if you transform 0, it gives you back 0. Lambda a, it scales. If you have a vector or anything and you scale it by lambda, then it will equal lambda, and then the transformation on a, and it's sort of like distributive with like addition. So LA plus B equals LA plus LB. So this is just all you need for a linear transformation, if I remember correctly. All right. So we have this linear transformation f prime x, which just approximates the function linearly at point x, and this acts on h, which is our change. And we also have this sort of error function o of h, just to give you a little bit of leeway to just to account for errors. And when you add these two, when you account for the errors, you get it describes this change of f of x plus h minus f of x. The book also added this sort of thing where like h is in the neighborhood around 0. So what we're in the single variable case, what typically happens is you get to this point right here, and then you just divide by h, so you get 2x plus h, and since the limit goes towards 0, h goes to 0, and so you just have 2x. Instead, we can recognize that this fits the description for this, and this doesn't, so it must be part of this linear transformation. Now, in a single variable, or like in the one dimension, a linear transformation is just, we're multiplying by a factor, by some scalar. In this case, it would be 2x. 2x is the scalar at any x. So our linear transformation is just, or f prime of x is just 2x. But in higher dimensions, what is this? If it's not the vector of steepest ascent, it is actually a covector, and this is why the dot product works, because the way a covector behaves is similar to the way it behaves exactly, actually, of the way like how a covector acts on a vector. So a covector is a linear transformation of the vector, and the way you can visualize it, there are way better videos that just tell you about vectors, but the way you can visualize it is just this sort of measuring stick that, like, you can sort of visualize it as a bunch of these lines, straight lines, that are a thickness, or like are spaced apart by 1 over what this covector says. So in this case, the height would be 0.5 and the width would be 1. So if you do 1, 1, this hits this line that goes 3. And you can have sort of like intermediate values. This is just to sort of show you. And it's more like a bunch of level curves, right? What this does is it gives you, it actually comes with a better visualization, because you can say that it's the covector here is just a local approximation of what the level curve is. If you don't know what a level curve is, here we go. It's just a way to visualize a multivariable function like that. So it's really actually useful to both, for visualizing the function even. And instead of like, for local minima and maximum, let's say you just have this dot right here. I think it also works better for a local minimum and local maximum. Same goes for like visualizing, conservative vector fields. If a vector field is conservative, if you say it's like a covector field, then all the contour lines, I imagine, I'm just postulating here, but if it's not conservative, instead of having like these connected contour lines, you would have some sort of disconnect here, right? And these are our contours, our level curves. They wouldn't actually be differentiable, right? So yeah, you can think of a covector as this sort of measuring stick. And so if you have a function, that goes from R2 to R, you have this covector of 2. And the way it measures it, like you can make sense of it, like it's the partial derivative of f in terms of x. That's it this way, and this axis. The same goes for the partial derivative of f in terms of y. That goes up. If you have one like g of t that equals g1, okay, g of t equals g1, g2, then its derivative is g1 prime, g2 prime. That also makes sense to me, at least. But like as I said before, the derivative is actually the Jacobian matrix. So if we actually have a function that goes from R2 to R2, you get this matrix, which is just a bunch of partial derivatives. And we can actually sort of make it more, make it smaller by sort of calling it like this. We have these dual vectors right here, which, we can say this is u and v. These are the sort of like, we put these in a vector and they sort of like expand to give you the matrix. If that sort of makes sense to you. Now, here's one of the best parts. One of the biggest revelations for me. Divergence. So, divergence notationally is nabla dot f, where f is a vector field. Now, if you say nabla is a dual vector, then you don't need the dot product, but keep it there, for notational purposes, or just type div f. Now, what I think is, and algebraically, this is the same as the divergence, because the divergence is, this sum, the sum of these two. Like, if xy goes to uv, then this is the divergence, the partial of u over the partial of v. The partial derivative of u in terms of v in respect to v plus the partial derivative of v with respect to y. Wait, no, let me say that again, sorry. The partial derivative of u with respect to x plus the partial derivative of v with respect to y. And this is algebraically the same as the trace of the Jacobian of f. Now, but this gives you a better sort of geometric interpretation of what is actually going on here. If you don't know your linear algebra, you can study up on it. But the trace, one of the properties of a trace, first of all, the trace is just the sum of these diagonal entries. But a trace gives you the sum of all the eigenvalues. And if you don't know what an eigenvalue is or an eigenvector, so basically any eigenvector is a vector that lies in these lines. So if you have a matrix or that acts on V, the transform, it just gives you lambda V. So, it's eigen things are basically, the sort of characteristic. Now, usually any matrix that isn't just a rotation will give you two eigenvectors. And so our trace would be this lambda 1 plus lambda 2. And a thing to notice is that it's this sort of tiny change in area. When you apply it, it gives you this change in area. We don't care about, it doesn't give you this, but we don't care about that because that is too small in when you zoom way in. And so the change in area, dA, is actually equal to the sum of these two vectors. So this gives you a new way to visualize divergence. Divergence, you can visualize it as this sort of change in area. Like if you have this sort of circle and it's being squished, sort of moved by this field, by all the vectors around it in this vector field, the divergence sort of gives you the change in that area. If it's 0, it probably means there's nothing going on or it's just a rotation. And a rotation that indicates curl, but we're not thinking of curl here. I don't even know, yet how curl would fit into this whole covector thing. But for divergence, this makes it easier to understand. You sort of have this. If it's positive, it's sort of expanding, it's getting stretched, and if it's negative, it's getting smooshed, it's getting squished. So yeah, let's do a quick recap. A derivative, this is the best definition for what a derivative is. It's just, a derivative is a linear transformation at x, that approximates that function. Linear transformation that approximates the function at x. Right? And it's sort of carried on by these two. The gradient is not, or the multivariable derivative is not the vector of steepest descent. It is the Jacobian. Alright? We can also visualize this covector as a bunch of contour lines or a bunch of level curves, right? And I don't know, but like I said before, it could also be useful for visualizing which fields are conservative and non-conservative. If instead of having, vector fields, you have a bunch of lines, and you see that they're not continuous, and then that would, give you a better idea of if it is or is not conservative, right? The Jacobian sort of works like this. You can look it up yourself. And this is a really cool fact about divergence. The divergence is just the trace of the Jacobian of the vector field. And that's all I have to say for now.